Tonight, we're going to take a journey, not a quick trip across a continent or even across an ocean. A journey so vast that the numbers involved stop making sense in ordinary human terms. A journey from where you are sitting right now, outward through the solar system, past every planet, past every moon, past the last outpost of sunlight strong enough to cast a shadow, all the way to the boundary where the sun's grip on space finally ends and something far stranger begins. This boundary is real. Spacecraft have crossed it. Instruments have measured what lies beyond it, and what those instruments found out there, billions of miles from the nearest star, has repeatedly stunned the scientists who dedicated their careers to understanding it. We are going to travel tonight through a solar system that is almost nothing like the orderly diagram you saw in a school textbook. Not a neat arrangement of 8 planets with tidy orbits and empty space between them. Instead, a layered, dynamic, violent, and extraordinarily complex structure stretching in every direction for distances that dwarf anything in human experience. A solar system filled with icy worlds, invisible clouds of ancient debris, regions where the sun's own wind collides with the galaxy itself and creates shock waves that no model fully predicted. By the end of tonight, you're going to understand what the solar system actually is, how it is structured from the inside out, why the regions beyond Neptune are among the most scientifically important and least understood places in our cosmic neighborhood, and what happens at the very edge, the place where the sun's influence ends and interstellar space begins. You're going to discover why that edge is not where scientists expected it to be, why its shape surprised everyone, why things out there behave in ways that no theory fully anticipated, and you're going to understand what it means that 2 spacecraft, launched in 1977 with technology less sophisticated than a modern microwave oven, actually made it to that edge and crossed it, and what they found when they got there. Before we get started, if you love exploring the outer reaches of our solar system as much as we do, take a second to like the video or subscribe. It costs nothing, but it genuinely helps this channel reach more people who are curious about the universe. Now, let's begin the journey. Start at the sun. Everything begins here. The sun is not a gentle, distant warmth. It is a thermonuclear furnace 865,000 miles across, containing 99.86% of all the mass in the entire solar system. Every planet, every moon, every asteroid, every comet, every dust grain, every spacecraft we have ever launched, all of it together adds up to less than 1/5 of 1% of the sun's mass. The sun is not just the center of the solar system in a geographical sense. It dominates the solar system the way a freight train dominates a flea. At the sun's core, the temperature is roughly 27 million degrees Fahrenheit. Under those conditions, hydrogen nuclei are forced together fast enough and hard enough that they fuse into helium, releasing energy in the process. Every second, the sun converts approximately 600 million tons of hydrogen into helium. Every second. The energy released by that fusion works its way outward through the sun's dense interior, a journey that can take hundreds of thousands of years before finally escaping from the visible surface as light and heat. But the sun doesn't just radiate light, it breathes constantly in every direction. What it breathes out is called the solar wind, a continuous stream of charged particles, mostly protons and electrons, that flows outward from the sun at speeds between 250 and 500 miles per second. Not every second, not when the sun is particularly active. All the time, continuously, 1 million tons of material per second, every second, streaming outward into space and washing over everything in the solar system. The solar wind is what makes comet tails always point away from the sun, regardless of which direction the comet is moving. It is what creates the auroras on Earth, and on Jupiter, and on Saturn, and on every other planet with a magnetic field. It is what presses against the magnetospheres of planets and sculpts them into teardrop shapes. And it is the solar wind, traveling outward in every direction, that ultimately defines the boundary of the solar system itself. But we are getting ahead of ourselves. Let's travel outward properly. Let's feel the scale. The first planet you encounter leaving the Sun is Mercury, at an average distance of 36 million miles. Mercury is a battered, airless, scorched world with temperature swings between 800 degrees Fahrenheit on the sunlit side and negative 290 degrees at night. It has almost no atmosphere to speak of because the solar wind stripped whatever it once had. At light speed, the journey from the Sun to Mercury takes just over 3 minutes. Keep going. Venus at 67 million miles. A world covered in thick sulfuric acid clouds with a surface temperature of 900 degrees caused by a runaway greenhouse effect. The most geologically active planet in the solar system, aside from Earth, with volcanoes and vast lava plains beneath that impenetrable cloud cover. Earth at 93 million miles, 1 astronomical unit. This is the measuring stick, the baseline from which all other solar system distances will be expressed. Everything you have ever seen, every person who has ever lived, every civilization that has ever risen and fallen, every war, every discovery, every birth and death in all of recorded history. It all happened here on this world at 1 astronomical unit from the Sun. Light from the Sun takes 8 minutes and 20 seconds to reach us here. Mars at 142 million miles, 1.5 astronomical units, a desert world with the largest volcano in the solar system, Olympus Mons, 3 times the height of Everest, and the longest canyon system, Valles Marineris, which would stretch from coast to coast across the United States. Signs in the ancient rock that liquid water once flowed there in quantity. Possibly, though not certainly, a world where life once began and then died as the planet lost its magnetic field and its atmosphere was stripped away by the solar wind. And here, at Mars, you have barely left the neighborhood. You are 1.5 astronomical units from the Sun. The solar system extends to roughly 100,000 astronomical units in its farthest reaches. You have traveled less than 2/10,000ths of the way. Past Mars, you enter the asteroid belt, a region between roughly 2 and 3.3 astronomical units from the Sun, where millions of rocky bodies orbit in a broad band. The asteroid belt is often depicted in movies as an impossibly dense field of tumbling rocks, ships weaving desperately through near-constant collisions. The reality is quieter and stranger. The asteroid belt is mostly empty space. If you launched a spacecraft through it, as many spacecraft have done, you would most likely pass through without hitting anything, simply because the total volume of the belt is so enormous and the rocks, while numerous, are also tiny compared to that volume. The total mass of everything in the asteroid belt is less than 4% of the mass of the Moon. The reason the asteroid belt exists at all, rather than having coalesced into a planet, is Jupiter. Jupiter's enormous gravitational influence stirred up the material in this region, preventing it from gathering. The rocks of the asteroid belt are primordial debris, leftovers from the formation of the solar system 4.6 billion years ago, material that never had the chance to build a planet. Some asteroid belt objects are spectacular in their own right. Ceres, the largest, is nearly 600 miles across. When the Dawn spacecraft visited it in 2015, it revealed a world with bright white salt deposits and craters, evidence of subsurface water ice, and a surprisingly complex geological history. Ceres is now classified as a dwarf planet, sharing its orbital territory with millions of smaller siblings. Continue outward through the asteroid belt and you begin to feel a change. The sunlight grows noticeably dimmer. At the outer edge of the asteroid belt, around 3.3 astronomical units, light intensity is only about 1/10 what it is at Earth. You are moving into a different kind of solar system. Colder, darker, governed less by sunlight and more by the deep cold of space. Jupiter at 5.2 astronomical units, the king of the planets, and it earns earns the title. Jupiter is 318 times the mass of Earth, more than twice as massive as all the other planets combined. It is a giant ball of hydrogen and helium gas with no solid surface, organized into ferocious bands of wind that blow in alternating directions at speeds exceeding 400 miles per hour. The Great Red Spot, a storm that has been raging for at least 350 years and possibly much longer, is a high-pressure system so large that Earth could fit inside it with room to spare. Jupiter has at least 95 confirmed moons as of recent counts. The 4 largest, discovered by Galileo in 1610, are worlds unto themselves. Io, the innermost, is the most volcanically active object in the entire solar system. It is constantly being flexed and squeezed by Jupiter's gravity and the gravitational tugs of the other moons, generating so much tidal heat that the interior is largely molten. There are more than 400 active volcanic centers on Io. Some of its eruptions are photographed from spacecraft at distances of hundreds of thousands of miles as enormous umbrella-shaped plumes rising nearly 200 miles above the surface. Europa, the second large moon, is covered in a shell of water ice that may be tens of miles thick. Beneath that ice, most planetary scientists now believe, is a global liquid water ocean kept liquid by tidal heating. The ocean may be 60 miles deep, deeper than any ocean on Earth. Its total volume likely exceeds all of Earth's oceans combined. And in that dark, tidally heated water, with chemistry driven by materials from the surface, cycling down through cracks in the ice, there is a real possibility that life exists. Not intelligent life, not complex animal life, probably, but microbial life, chemistry doing interesting things in water, warmed by gravity. Europa is one of those compelling targets in the search for life in the solar system. Ganymede, the largest moon in the solar system, bigger than the planet Mercury, has its own magnetic field, a distinction shared by no other moon anywhere. Callisto, the outermost of the Galilean moons, is one of the most heavily cratered surfaces in the solar system, an ancient record of the violent bombardment that characterized the early solar system. Jupiter is not just a destination. It is a gravitational force that shapes the entire solar system. It deflects comets inward toward the inner planets and outward into deep space. It may have played a crucial role in delivering water to early Earth by scattering icy bodies from the outer solar system into the inner regions during the early history of the solar system. It protected the inner solar system from some of the worst bombardment by catching certain impactors in its own gravity. Jupiter is the architect and the gatekeeper of the solar system's inner regions. Saturn, at 9.5 astronomical units, nearly 900 million miles from the Sun. Light from the Sun takes 80 minutes to reach it, and Saturn is where the solar system begins to reveal itself as truly alien, truly different from anything in the inner regions. The rings. You have seen photographs. Photographs do not prepare you for the reality. Saturn's ring system stretches 175,000 miles from edge to edge, wide enough to fit 6 Earths side by side, yet the rings are extraordinarily thin, in most places no more than about 30 feet thick. If you scaled Saturn down to the size of a basketball, the rings would be thinner than a sheet of paper relative to their width, a structure of almost inconceivable thinness, made of billions of individual particles, ranging from specks of dust to chunks the size of houses, all orbiting Saturn at precisely determined speeds according to the laws of orbital mechanics. The rings are not a single structure, but thousands of individual ringlets, each one a slightly different orbit, separated by gaps carved by the gravitational resonances of Saturn's moons. Shepherd moons, tiny satellites like Prometheus and Pandora, orbit at the edges of certain rings and gravitationally confine the ring particles with extraordinary precision. The F ring, confined by these shepherds, is braided and knotted in ways that took years of observation to partially understand. Spokes appear and disappear in the rings, dark radial features that rotate with Saturn's magnetic field caused by electrostatic levitation of fine dust particles. Saturn's largest moon, Titan, is the only moon in the solar system with a thick atmosphere. Its surface pressure is 1.5 times Earth's. Its atmosphere is mostly nitrogen, as Earth's is, but the similarities stop there. The temperature on Titan's surface is negative 290 degrees Fahrenheit, cold enough that methane exists as a liquid. There are lakes and seas of liquid methane and ethane on Titan's surface. There are rivers and streams that flow with liquid hydrocarbons. There are clouds of methane that rain hydrocarbon droplets. Titan has a complete hydrological cycle, just like Earth, but driven by methane instead of water, operating at temperatures that would freeze any Earth creature solid in seconds. The Cassini spacecraft orbited Saturn for 13 years, from 2004 to 2017, and every year produced new surprises. Geysers on Enceladus, a small moon spewing water vapor and ice particles from a subsurface liquid water ocean. A hexagonal storm at Saturn's North Pole, a geometric vortex of clouds 6 times wider than Earth that has persisted for decades. Gravity waves in the rings driven by oscillations deep inside Saturn itself, allowing scientists to probe the planet's interior the way doctors use ultrasound to image internal organs. When Cassini finally exhausted its fuel, mission controllers deliberately plunged it into Saturn's atmosphere, destroying the spacecraft rather than risk contaminating any moon with terrestrial microbes. Cassini died giving its last measurements of Saturn's atmosphere, transmitting data until the atmospheric pressure finally overwhelmed its communications. It was a fitting end for a spacecraft that had spent 13 years revealing Saturn to be far more extraordinary than anyone expected. Uranus, at 19.2 astronomical units, nearly 1.8 billion miles from the Sun. Light takes 2 hours and 40 minutes to get here, and Uranus is where the solar system starts to feel genuinely remote. Uranus is the only planet in the solar system that rotates on its side. Its axial tilt is 98 degrees, nearly perpendicular to its orbital plane, which means it rolls around its orbit more like a barrel than like a spinning top. Scientists believe this tilt was caused by a massive collision early in the solar system's history, a glancing blow from a body roughly the size of Earth that knocked Uranus onto its side. Whatever that impactor was, it hit hard enough to permanently alter the spin axis of a planet that is 63 times the volume of Earth. This extreme tilt has bizarre consequences for seasons. Each pole points directly at the Sun for roughly 21 years at a time, then points directly away from the Sun for another 21 years. During polar summer on Uranus, the pole receives more total sunlight than the equator does. During polar winter, it receives none at all. The Voyager 2 spacecraft flew past Uranus in January 1986. Only one spacecraft has ever visited this planet. Everything we know about Uranus from direct measurement comes from that single flyby and from Earth and Space Telescope observations. Voyager 2 discovered 10 previously unknown moons and found that Uranus has a faint ring system. It measured magnetic fields behaving strangely, offset from the planet's center and tilted at 60 degrees from the rotation axis. a geometry unlike any other planet in the solar system. It photographed the Uranian moons in detail for the first time, finding Miranda with its bizarre geology of cliffs and ridges and chasms, evidence of some violent or complex geological history that scientists are still debating. A proposed future mission to Uranus, recommended as the top priority for large missions in the most recent planetary science decadal survey, would take more than a decade to build and launch, and another decade or more to travel there. The earliest we might have an orbiter at Uranus is the mid-2040s. In the meantime, our single set of 1986 measurements is all we have. Neptune at 30 astronomical units, 2.8 billion miles from the Sun. Light takes 4 hours to make the trip. In terms of volume, Neptune is the farthest of the 8 major planets, the outer limit of what textbooks call the solar system. But in terms of actual distance covered, you are still only a tiny fraction of the way to the real edge. Neptune is in some ways the most dynamic planet in the outer solar system, despite being so far from the Sun that it receives 900 times less sunlight than Earth. Neptune has winds exceeding 1,300 miles per hour, the fastest measured on any planet. The source of this energy is not sunlight. Neptune radiates about 2.6 times more heat than it receives from the Sun, drawing on some internal heat source, possibly the slow gravitational compression of its interior, to drive those ferocious winds. When Voyager 2 flew past in 1989, 12 years after launch, it found a great dark spot in Neptune's southern hemisphere, a storm system comparable in size to Earth. By the time the Hubble Space Telescope looked at Neptune a few years later, the great dark spot had vanished. New storms had formed in the north. Neptune's atmosphere is dynamic and changeable in ways that mock the idea of a cold, static outer planet. Triton, Neptune's largest moon, orbits backward, retrograde orbit, opposite to Neptune's rotation. No moon of any planet formed alongside its parent planet orbits in reverse. This means Triton was captured. It was not born at Neptune. It wandered in from somewhere else in the outer solar system, perhaps the Kuiper Belt, and was gravitationally captured by Neptune billions of years ago. The capture process would have been enormously violent, disrupting any previous moon system Neptune possessed. Triton has geysers on a world where the surface temperature is negative 391 degrees Fahrenheit, one of the coldest surfaces anywhere in the solar system. Nitrogen geysers erupt, carrying dark particles of material high into the thin atmosphere and depositing them as dark streaks downwind. The mechanism is subtle and elegant. Sunlight, feeble though it is at this distance, manages to penetrate the translucent nitrogen ice and warm, dark regions beneath. The nitrogen sublimates directly from solid to gas. Pressure builds, and eventually the pressure ruptures the surface, venting nitrogen that carries dark material upward before falling back to paint the surface. An ocean world with geysers erupting from a surface of minus 391 degrees ice, orbiting backward around a planet it was captured by billions of years ago. The solar system's capacity for strangeness does not diminish with distance. It grows. But here is where most textbooks end. Here is where most people's mental map of the solar system stops. 8 planets, 4 rocky, 4 gas giants, and beyond Neptune, empty space stretching to the nearest star. This picture is wrong, profoundly and magnificently wrong. Beyond Neptune lies a solar system more populous, more complex, and more scientifically rich than everything we have covered so far combined. Welcome to the outer solar system, the part almost no one knows exists. The Kuiper Belt begins at roughly 30 astronomical units, where Neptune orbits, and extends to about 50 astronomical units. It is a broad disk of icy bodies, remnants from the formation of the solar system that were never incorporated into a planet. The Kuiper Belt contains hundreds of thousands of objects larger than 60 miles across, and perhaps 1 trillion or more smaller objects. The Kuiper Belt is not empty space punctuated by occasional rocks. It is a zone. A structured region with its own internal organization, shaped by the gravitational influence of Neptune into populations of objects in specific orbital resonances. Objects in the 2 to 3 resonance with Neptune, orbiting the Sun exactly twice for every 3 of Neptune's orbits, are called Plutinos. Pluto is the most famous of these. Pluto. For 76 years after its discovery in 1930, Pluto was classified as the 9th planet. In 2006, the International Astronomical Union reclassified it as a dwarf planet, a decision that generated more public controversy than almost any other in the history of astronomy. But regardless of how you classify it, Pluto is one of the most interesting worlds in the outer solar system. The New Horizons spacecraft flew past Pluto in July 2015 after a journey of 9 years and more than 3 billion miles. What it found there astonished scientists. Not a dead, cratered ball of ancient ice, a geologically active world, still changing today. The surface of Pluto has regions younger than 10 million years old, which on geological timescales is virtually yesterday. Nitrogen glaciers flow slowly across the surface. Mountains of water ice rise 11,000 feet from the plains. Vast, smooth plains, now called Tombaugh Regio, were formed by convection in a nitrogen ice layer, the same fundamental process driven by internal heat that drives tectonic activity on Earth. Pluto's atmosphere, tenuous but real, extends thousands of miles above the surface and turns brilliant shades of blue when backlit by the sun, caused by the same kind of light scattering that makes Earth's sky blue. Pluto has mountains capped with methane ice deposits that evaporate in the warmth of Plutonian summer and redeposit somewhere else. Pluto has canyons and plains and possible evidence of ancient liquid water oceans. Pluto has 5 moons. The largest, Charon, is so large relative to Pluto that the two form a true binary system, each orbiting the other's gravity around a point in the space between them. Charon has a red polar cap made of material that escaped from Pluto's atmosphere and froze onto Charon's surface. The system is extraordinary in its complexity. Beyond Pluto, in the outer Kuiper Belt, other dwarf planets orbit the Sun. Eris, roughly the same size as Pluto, was discovered in 2005, and its discovery was the direct trigger for the debate over Pluto's classification. Haumea, shaped like a flattened egg and spinning so fast that it completes one rotation in under 4 hours. Quaoar, Sedna, one of the most distant known solar system objects, with an orbit that takes it as far as 936 astronomical units from the Sun. Each of these worlds, visited by no spacecraft, known in most cases only from telescope observations, represents a separate chapter in the solar system's history. They are time capsules from the early solar system, frozen records of the conditions and processes that shape the planets we know. Understanding them is not a luxury. It is essential for understanding where the solar system came from. At around 50 astronomical units, the main Kuiper Belt gives way to what scientists call the scattered disk, a population of objects in highly elliptical orbits that were scattered outward by gravitational interactions with Neptune early in the solar system's history. Objects in the scattered disk spend most of their time in the extreme outer solar system but plunge periodically inward, sometimes as comets. Many of the comets that visit the inner solar system, the ones that streak across our sky with brilliant tails, are scattered disk objects that were gravitationally nudged onto a trajectory toward the Sun. The scattered disk merges gradually and uncertainly into an even more remote structure, one that is not well mapped and not well understood, a region where individual objects have been found far beyond the main Kuiper Belt in orbits that defy easy explanation. Sedna's orbit, for example, cannot be explained by any current known gravitational influence in the solar system. Its perihelion, its closest approach to the Sun, is 76 astronomical units. Nothing currently in the inner solar system could have pushed it to such a remote orbit. The leading explanation is that Sedna was scattered outward during an early period when the Sun was still in its birth cluster of stars, and the gravity of those other stars perturbed its orbit into its current extreme configuration. Another explanation, currently controversial but actively discussed, is that an as yet undiscovered large planet in the extreme outer solar system, sometimes called Planet 9 or Planet X, is responsible for the strange orbital clustering observed among several extreme Kuiper Belt objects. Planet 9, if it exists, would be roughly 10 times the mass of Earth and would orbit at hundreds of astronomical units from the Sun. It has not been directly observed. Its existence is inferred from statistical patterns in the orbits of known extreme outer solar system objects, a kind of gravitational detective work. The evidence is suggestive, but not conclusive. Surveys searching for this hypothetical object are ongoing. It may be found in the next decade. It may not exist at all. Either answer would be scientifically important. Finding it would reveal a major previously unknown component of the solar system. Not finding it, despite thorough searches, would require an alternative explanation for the orbital patterns that currently point toward it. At 100 astronomical units, you are 10 times farther from the Sun than Neptune. Light from the Sun takes nearly 14 hours to reach you here. The Sun itself, if you could see it from here, would appear as a very bright star. Brighter than any other star by a vast margin, but clearly a star rather than the blazing disk you see from Earth. At this distance, solar radiation pressure is negligible. The solar wind has lost most of its coherent structure. This is the region that the Voyager spacecraft are now traversing. Voyager 1, launched in 1977, crossed the 100 astronomical units mark years ago. In 2026, it is at approximately 159 astronomical units from the Sun and still transmitting, still returning data, still teaching us things about the outer solar system that no other instrument can. But before Voyager crossed to interstellar space, it had to navigate the Heliosphere. The Heliosphere is the bubble of space dominated by the Sun's influence. Its outer boundary is not the orbit of Neptune or the edge of the Kuiper Belt. Its outer boundary is where the solar wind, after traveling billions of miles, finally exhausts itself against the pressure of the interstellar medium, the thin gas and dust that fills the space between the stars. Think of the Heliosphere as a soap bubble blown by the Sun into the interstellar medium. The solar wind inflates it. The interstellar medium presses back. The equilibrium between these two pressures defines the size and shape of the bubble. And this bubble, it turns out, extends far beyond the Kuiper Belt, far beyond even the scattered disk. The heliosphere reaches to roughly 120 astronomical units in the direction the Sun is moving through the galaxy, and possibly much farther in other directions. Before reaching that outer boundary, the solar wind encounters a transition called the termination shock. This is where the solar wind, which has been traveling outward at supersonic speeds, hundreds of miles per second, suddenly slows to subsonic speeds. The slowdown is abrupt and physically dramatic. The plasma heats up. It compresses. The density increases sharply, and energetic particles are accelerated by the shock to high energies, boosted up in the same way that a surfer is accelerated when a wave hits shallow water and steepens. The termination shock was a theoretical prediction for decades. No spacecraft had ever reached it. Models placed it at roughly 75 to 90 astronomical units. Voyager 1 crossed it in December 2004 at 94 astronomical units. Already 4 to 19 astronomical units farther out than models predicted. The boundary had been pushed outward by the pressure of a particularly strong solar wind period. The termination shock, it turned out, is not a fixed boundary. It breathes. It moves in and out in response to fluctuations in the solar wind, sometimes by several astronomical units in a matter of months. Voyager 2 crossed the termination shock in August 2007 at 84 astronomical units. 10 astronomical units closer than Voyager 1 crossed it, despite heading in roughly the same general outward direction. This discrepancy was a critical observation. If the heliosphere were symmetric, both spacecraft should have crossed at roughly the same distance. They didn't. The heliosphere is not symmetric. It is distorted by the Sun's motion through the interstellar medium, compressed in the direction of travel, stretched out behind. The shape is more like a comet or a teardrop than a sphere. Models had predicted some asymmetry but significantly underestimated its magnitude. Between the termination shock and the heliopause, the true outer boundary of the heliosphere, lies a region called the heliosheath. This is the outermost layer of the solar wind. The plasma here has been slowed, heated and compressed by the termination shock. It no longer flows simply outward. It flows outward but also sideways, deflected by the pressure of the interstellar medium, trying to flow around the obstacle. The flow in the heliosheath is turbulent, filled with magnetic field irregularities and plasma instabilities. Scientists expected the heliosheath to be 10 to 20 astronomical units thick, a transition zone through which Voyager would pass in a decade or less, before emerging into interstellar space proper. What they found was stranger. As Voyager 1 moved through the heliosheath in the years following 2004, it detected something unexpected. Galactic cosmic rays, high-energy particles from supernova explosions throughout the galaxy, were increasing in intensity. This was expected at the heliopause. But by 2010, cosmic rays were rising while the spacecraft was still clearly in the heliosheath, and low-energy particles of solar origin were declining. The boundary seemed to be doing strange things before Voyager got there. Then in 2012, Voyager 1 detected something that had no name in any model. A region where magnetic field lines aligned in perfectly organized radial patterns. pointing straight outward from the sun. Particles were flowing along these field lines in both directions simultaneously. Solar particles flowing outward, galactic cosmic rays flowing inward. The field lines were acting like a conduit, connecting the heliosheath directly to the interstellar medium, allowing particles to flow freely in both directions even though the boundary itself hadn't been crossed. Scientists called it the magnetic highway. No theoretical model had predicted it. No simulation had produced it. It appeared to be a region where the sun's magnetic field was linking up with the galactic magnetic field, field lines merging at the boundary and creating pathways for particle transport in both directions. The magnetic highway was a new phenomenon discovered not in a laboratory, but in the actual boundary region between the solar system and the galaxy. Voyager spent 2 months in the magnetic highway. Then, on August 25, 2012, the readings changed abruptly. Low-energy solar particles essentially disappeared. Galactic cosmic rays jumped to a new, stable, high level. The change happened over a few days. Voyager 1 had crossed the Heliopause. The debate that followed was one of the most vigorous in planetary science in decades. Some scientists said yes, Voyager had crossed into interstellar space. Others noted that the magnetic field direction hadn't changed. The sun's magnetic field and the galactic field appeared to be pointing in the same direction, which confused things. How could you have crossed from one domain to the other if the magnetic field didn't rotate? The answer, worked out over the following year, was a coincidence. The local galactic magnetic field in the region Voyager 1 crossed happened to be pointing in nearly the same direction as the sun's field, not because they are aligned fundamentally, but because the specific patch of interstellar medium the sun is currently moving through has its magnetic field pointed that way. Had Voyager crossed in a different direction, the field rotation would have been obvious. In September 2013, NASA officially announced that Voyager 1 had entered interstellar space on August 25, 2012. The crossing had occurred at 121 astronomical units. Models had predicted 90 to 100. The heliopause was 20 to 30% farther out than the most sophisticated simulations expected. The interstellar medium in our current neighborhood, it turned out, exerts less pressure on the heliosphere than previously assumed. The sun's bubble is bigger than we thought. Voyager 2 crossed the heliopause on November 5, 2018, at 119 astronomical units. Voyager 2 made the first and so far only direct measurements of the plasma in the interstellar medium at the moment of crossing. It detected a sharp increase in plasma density and a clear change in the plasma temperature as it passed through the heliopause. The boundary was thin, just a few astronomical units thick, sharper and more distinct than many models had suggested. The measurements from both spacecraft were stunning in their implications. The Heliosphere is bigger than expected. Its shape is more asymmetric than expected. The transition across the heliopause is more complex and layered than expected. And the interstellar medium beyond it has properties that differ from predictions in multiple measurable ways. Beyond the heliopause, Voyager 1 and Voyager 2 are now sampling the local interstellar medium, the space between the stars, the environment that our solar system is moving through. The density is about 0.08 particles per cubic centimeter. That sounds negligible, and compared to any earthly gas, it is incomprehensibly thin. But compared to the perfect vacuum of the inner heliosphere, it represents real material, real particles, real magnetic fields, real structure. The temperature of the interstellar plasma is surprisingly high, tens of thousands of degrees in thermal terms. But because the density is so low, the temperature represents almost no heat content. An astronaut in the interstellar medium would freeze, not burn. Temperature is a measure of the energy of individual particles. With so few particles, the thermal energy per unit volume is essentially nothing. Voyager 1 detected plasma wave oscillations in the interstellar medium, waves of compression traveling through the thin plasma. Measuring the frequency of these waves allowed scientists to calculate the electron density of the interstellar medium with unexpected precision. The density matched predictions reasonably well, but the variations in density, region to region, were larger than expected. The interstellar medium is not uniform. It is structured, patchy, variable in ways that the 2-point measurements from the Voyagers only hint at. Both spacecraft detected something remarkable. Tsunami waves, massive pressure pulses launched outward by powerful solar storms, coronal mass ejections of unusual violence that traveled across billions of miles of space, crossed the Heliopause and produced detectable compression waves in the interstellar medium. The first was detected in October and November of 2012, just weeks after Voyager 1's crossing. Others followed in 2013, 2014, and 2015. These detections were completely unanticipated. Scientists had not expected the sun's outbursts to be detectable as shock waves in interstellar space. A solar storm that happened on Earth's side of the sun, billions of miles away, launched a pressure pulse that crossed the entire solar system, crossed the Heliopause, and was detected by a spacecraft in interstellar space. The sun's influence extends far beyond the heliosphere in ways that models had not accounted for. The galactic magnetic field measured by both spacecraft was also surprising. The field is real and measurable, about 50 nanoteslas in strength, an almost incomprehensibly faint magnetic field 1,000,000 times weaker than Earth's. But it is there, and it is structured. The direction it points differs between the two spacecraft's crossing locations, even though those locations are only about 121 astronomical units apart. The local galactic field is not uniform on scales of 100 astronomical units. It varies. It has structure. Understanding that structure is important because it controls how galactic cosmic rays travel through the galaxy and how they penetrate into the heliosphere. The cosmic rays themselves were measured in detail at both crossing points. The intensity in interstellar space is about 10 to 20% higher than in the outer heliosheath. The heliosphere provides measurable shielding against galactic cosmic rays. And the directionality of those cosmic rays, the directions they come from, showed anisotropies, preferential directions, that no simple model had predicted. The local cosmic ray environment has structure beyond what a simple isotropic galactic background would produce. Some of this structure may reflect nearby supernova remnants or other local sources. Some may reflect the guiding effect of the local galactic magnetic field. Every measurement the Voyagers have made in interstellar space has refined our picture. and every refinement has shown that the real universe is more textured, more structured, more dynamic than the models it replaced. Beyond the Heliopause, the solar system does not end. Not really. The Sun's gravitational influence extends much farther than the heliosphere. Gravity falls off with distance but never reaches zero. The Sun's gravity controls objects out to roughly 100,000 to 200,000 astronomical units, nearly halfway to the nearest star. In this vast outer region, from perhaps 2,000 to 100,000 or more astronomical units, lies the Oort cloud. It is, in a sense, the true outer solar system, a spherical shell, not a flat disk like the Kuiper Belt, of perhaps hundreds of billions to trillions of icy objects surrounding the Sun in a vast halo. We have never directly observed the Oort cloud. We infer its existence from long-period comets, objects that arrive in the inner solar system on trajectories coming from random directions in the sky, rather than from the flat orbital plane of the planets. Their trajectories trace back to a spherical source region thousands of astronomical units distant. The Oort cloud objects are original solar system material, formed closer to the Sun early in the solar system's history, and then gravitationally scattered outward by the giant planets over billions of years. They sit in stable, very slowly evolving orbits at enormous distances, periodically disturbed by gravitational tugs from passing stars, from the galactic tide, from the collective gravity of the galaxy's disk, and launched occasionally onto trajectories that carry them inward to become the spectacular long-period comets that have thrilled and terrified humans throughout history. The Oort cloud has never been directly observed. No spacecraft has reached it. Voyager 1 will not reach the inner edge of the Oort cloud for approximately 300 years. It will not exit the outer edge for approximately 30,000 years. In the meantime, the Oort cloud remains the most vast and least explored component of the solar system, inferred but not seen, a theoretical structure supported by strong indirect evidence but without a single confirmed direct observation of one of its members. Understanding the Oort cloud is not just a curiosity. The Oort cloud is the ultimate source of many of the comets that have struck Earth throughout its history, and comet impacts have played significant roles in Earth's history, possibly delivering organic molecules, certainly causing some of the mass extinctions recorded in the fossil record. The Oort cloud is where the solar system keeps its most ancient, most pristine material, objects that have been frozen and unchanged since the solar system formed 4.6 billion years ago. Comets from the Oort cloud carry samples of the original nebula from which the Sun and planets formed. The Voyagers are extraordinary machines. They were launched in 1977, 49 years ago as of 2026. Each one weighs 1,820 pounds and carries instruments designed with slide rules and programmed with computers that had 68 kilobytes of memory combined. Less than a modern digital wristwatch. Their power source is the slow radioactive decay of plutonium-238, and by 2026 the power available on each spacecraft has dropped to roughly 250 watts, barely enough to run a few instruments and the transmitter. Engineers have spent years carefully shutting down heaters and instruments to keep the remaining systems alive within an ever-shrinking power budget. The signal from Voyager 1 takes 22 hours and 35 minutes to reach Earth. When scientists on the ground send a command, they wait nearly 2 days for the round trip. The spacecraft's antenna is pointed at Earth by gyroscopes and attitude control thrusters that must be carefully managed to preserve the remaining propellant. In 2013, mission controllers switched Voyager 2 to backup thrusters that had not been fired in 37 years. They fired perfectly. By the late 2020s, there will not be enough power remaining to operate any science instruments. The transmitters will eventually fall silent, probably before 2030. When that day comes, the solar system will lose its only eyes at the edge of interstellar space. But the spacecraft themselves will continue. There is no friction in deep space, nothing to slow them down. They will travel outward forever, or until they happen to encounter something. Voyager 1 is heading toward the constellation Ophiuchus. In about 40,000 years, it will pass within 1.6 light-years of a star called Gliese 445. That is the closest it will come to any star for the foreseeable future. 1.6 light-years. Still not close enough to interact gravitationally. Just passing through, drifting in the cosmic void. Attached to each spacecraft is a golden record, a 12-inch gold-plated copper disc containing sounds and images from Earth, a message to whatever civilization might ever recover these spacecraft in the unimaginably distant future. The records contain music from many cultures and many eras, greetings in 55 languages, natural sounds of Earth, scientific diagrams encoded as audio. The cover carries pictograms explaining how to play the record, a pulsar map locating our sun, diagrams of human anatomy. The chance of these records ever being found is essentially zero. The galaxy is incomprehensibly vast, but they are out there, traveling, carrying a message from Earth into interstellar space for as long as the universe lasts. So, what is the solar system? After this journey from the sun's corona to the edge of interstellar space and beyond, to the vast outer cloud of ancient icy bodies, what is it? The solar system is not the 8 planets and their moons that fit on a poster. The solar system is a structured, layered, dynamic, evolving system spanning distances that take light years to traverse at its extremes. It contains hundreds of thousands of objects larger than 60 miles across, beyond Neptune alone. It is bounded not by a definite wall, but by a fuzzy, moving, breathing, asymmetric boundary between the sun's wind and the galaxy's medium. It contains regions discovered only in the last few decades and other regions we have never directly observed at all. It contains objects that are geologically active at the farthest reaches of sunlight, moons with oceans of liquid water warmed by gravity rather than sunlight, worlds with complex chemistry and weather systems in places where the sun is a barely distinguishable bright star. The edge of the solar system is not where textbooks say it is. The solar system extends to 100,000 astronomical units under the sun's gravitational influence. The Heliosphere, the sun's atmospheric bubble, extends to more than 120 astronomical units. Both are larger than the best models predicted, and both have structures and properties that models failed to anticipate. The boundary between the solar system and interstellar space is not a clean line. It is a transition zone with multiple layers, a termination shock where the solar wind slows, a heliosheath where it tumbles and turns, a magnetic highway where field lines connect the two domains, and a heliopause where solar plasma finally gives way to the thin gas of the galaxy. The transition took years for Voyager 1 to traverse. Its details were a surprise at every stage. The interstellar medium beyond the heliopause is not empty space. It has density, temperature, magnetic fields, cosmic rays arriving from every direction with anisotropies shaped by local sources, and the galactic magnetic field structure. It has pressure waves launched by solar storms. It has structure on scales from astronomical units to light years that our 2-point measurements from 2 aging spacecraft have only begun to map. The journey from the Sun to the edge of the solar system and beyond is a journey through scale, through distances that dwarf human experience so completely that they require their own framework of reference. 1 astronomical unit is 93 million miles. The orbit of Neptune is 30 astronomical units. The heliopause is 120 astronomical units. The inner Oort cloud begins at perhaps 2,000 to 5,000 astronomical units. The outer Oort cloud extends to perhaps 100,000 to 200,000 astronomical units. The nearest star is 268,000 astronomical units away, 4.24 light years. Voyager 1 has been traveling for nearly 50 years. It has covered 159 astronomical units. At this speed, it would take approximately 73,000 years to reach Proxima Centauri. And Proxima Centauri is the nearest star. The average distance between stars in our galaxy is about 1 million times the distance from Earth to the Sun. Interstellar space is not just far away. It is a different category of far than anything the human mind has natural intuitions for. And yet the knowledge we have gained from understanding the solar system's edge has implications that reach far beyond astronomy. Understanding the heliosphere and how it shields the inner solar system from galactic cosmic rays is relevant to understanding cosmic ray exposure on Earth, which influences atmospheric chemistry, possibly cloud formation, and has affected mutation rates and biological evolution over geological timescales. Understanding the heliopause and the interstellar medium is directly relevant to planning future interstellar probes, which must cross both these regions during any journey to another star. The conditions Voyager measured in interstellar space, the particle radiation, the magnetic field, the plasma density, tell us directly what future spacecraft will face. At Voyager's speed, those conditions are manageable. At the speeds needed for practical interstellar travel, the impacts of interstellar medium particles become significant. At 10% of the speed of light, a hydrogen atom hitting a spacecraft delivers enough energy to cause real radiation damage. Designing a spacecraft for interstellar travel requires understanding precisely the environment it will traverse. The Voyagers gave us the first direct measurements of that environment. The future of solar system edge exploration looks toward an interstellar probe mission, a concept studied extensively by NASA and the scientific community. The proposed design would use a solar gravity assist, swinging close past the Sun to use its gravity as a slingshot to reach speeds 2 to 3 times Voyager's. The goal is to reach 1,000 astronomical units within 50 years, more than 6 times farther than the Voyagers have reached in nearly the same time. At 1,000 astronomical units, the spacecraft would be deep in the outer heliosphere and beginning to characterize the structure of the interstellar medium on larger scales. Such a mission would carry instruments far more capable than the Voyagers. Modern plasma analyzers, magnetometers, energetic particle detectors, neutral atom imagers that could map the three-dimensional structure of the heliosphere from the outside rather than traversing one line through it. It would carry cameras capable of looking back at the solar system from hundreds of astronomical units and producing images of the heliosphere that no human has ever seen. But the mission has not yet been approved. No budget has been allocated. No launch date exists. Even if the mission were approved today, it would take a decade to build and launch. The science of the solar system's edge will continue to rely, for now, on the two aging, dimming, extraordinary Voyager spacecraft until a new generation of missions finally follows in their trail. There is something genuinely moving about understanding what lies at the edge of the solar system. Not just the science, though the science is astonishing. Something more personal than that. When you look up at the night sky and see the sun's light reflected off the planets, when you follow the arc of a comet or watch the Milky Way stretch across a dark sky, you are seeing the interior of a structure that extends far beyond what your eyes can reach. You are inside the heliosphere. The sun's wind is streaming past you at hundreds of miles per second, and you cannot feel it because your atmosphere shields you. The termination shock is out there beyond Neptune, beyond Pluto, beyond the farthest object anyone has named or catalogued. The heliopause, the true edge of the sun's domain, is so far away that the light from the sun reaching that boundary right now left the sun 14 hours ago. And beyond the heliopause, in interstellar space, two small machines launched by human hands are drifting. Machines built with technology that seems laughably primitive by modern standards. Machines that have exceeded every expectation of their designers by a margin that no one anticipated. Still transmitting, still measuring, still, after nearly 50 years, returning new data about a boundary that no other instrument has crossed. The Voyagers carry golden records, messages from Earth into the void. But they themselves are the more profound message, not the sounds and images encoded on the disks, the spacecraft themselves. Two objects made of human ingenuity and human stubbornness and human curiosity crossing into interstellar space, demonstrating that a species that evolved on one small rocky planet around one ordinary star has reached out beyond the boundary of its own solar system. The journey to the edge of the solar system is not just a physical journey through space. It is a journey through the history of scientific understanding, from the ancient world's picture of a cosmos centered on Earth and bounded by a sphere of stars, through Copernicus and Kepler and Newton, through the telescopic revolution that revealed the planets as worlds and the stars as distant suns, through the space age that sent machines to visit those worlds and sample their surfaces and fly through their upper atmospheres, all the way to Voyager at the Heliopause, measuring the local interstellar medium while its transmitter output, barely 22 watts of power, carries its signal across 14 billion miles to antennas 230 feet across, waiting patiently in the California desert, the Australian plains, the Spanish plateau. The solar system is larger than we knew. Its edge is farther, stranger, more complex than our models predicted. The space beyond it is more structured and more dynamic than we expected. And everything we have learned about it has come from instruments, from mathematics, from physics, from the cumulative effort of thousands of scientists over many decades pushing back the boundary of the unknown, one measurement, one discovery, one surprise at a time. That is the journey to the edge of the solar system, and we have barely begun.